Hi everyone, welcome to our presentation. We'll do this presentation jointly with all the authors of the work to reflect the collaborative nature of the work across 3 different research groups, spanning evolutionary algorithms, theory, benchmarks, and machine learning. In particular, we would like to tell you about theory-inspired parameter control benchmarks for dynamic algorithm configuration, or in short, when theory is useful to benchmark reinforcement learning methods. As we all know, algorithm parameters are everywhere. For example, here's just a small selection of the parameters of CMAS. And generally, the setting of such parameters strongly affects the performance of our algorithms. Parameters are also very important in many other fields, maybe most prominently in the field of deep learning, where they include many different architectural choices and choices in the training and regularization pipeline, such as learning rates, etc. Now, how do we deal with algorithm parameters? Well, one prominent approach in the literature, known as algorithm configuration, is to search in a big space of possible configurations for the one configuration with the best performance on average for a distribution of problem instances. Another prominent solution is algorithm selection, where we look at the instance at hand and select the configuration or algorithm that we think will work best for this particular instance. And in this work, we study the third, very exciting framework of parameter control, where we're looking for the best way to adapt a configuration at runtime. One nice feature of parameter control that we draw on in this work is that there's a lot of theory on the optimal adaptation strategy. However, parameter control strategies tend to be manually defined, and next, Andre will tell you a bit more about how we can learn these parameter control strategies from data.
Dynamic algorithm configuration is an exciting new field that combines the strengths of the previous frameworks. In order to learn dynamic configuration policies from data, we need to observe the following. First off, we need some features that tell us how the algorithm has progressed. For example, if we can see that it does not make large or even any progress right now, we might want to change the parameters to again make some progress. This gives us a local view on the optimization landscape. Secondly, we need to observe some characteristics of the problem instance at hand. These features give us a more global view on the optimization problem and can help us in the end to transfer policies better. Together, this information enables us to learn configuration policies that adapt parameters on the fly, but also to the instance at hand. And in practice, we learn DDQN policies in an offline training phase via reinforcement learning. Now, with new research field, there comes exciting challenges and opportunities. And in particular, here we care about how to evaluate and benchmark DDQN methods. We have already seen that DDQN has had great successes, for example, on toy benchmarks, evolutionary algorithms, and AI planning, where the learned policies beat even the best theoretical algorithm selector. However, these applications are not the best for benchmarking DDQN. Often the benchmarks are very expensive and, most importantly, do not come with ground truth. Thus, it is difficult to judge if the learned policies are capable of reaching the best performance. Counter to these benchmarks, we draw on the rich theory of parameter control to propose novel benchmarks that have low cost and provide us with ground truth. Next up, Martin will tell you more about these benchmarks.
Our benchmarks are a combination of an objective function from theory, namely LeadingOnes, and of variants of randomized local search. Each of these algorithms has a configurable parameter R, the search radius, which tells us in what vicinity the algorithm tries to look for better solutions. And the nice thing about these two aspects is that in combination they're theoretically perfectly understood. So that means that we have exact guarantees for the entire runtime distribution of these algorithms on this specific function. This also entails that we know the exact expected runtime of these algorithms or their exact variance. And we can exploit this information in order to state rules that tell us how to map different algorithm states to different search radii. For example, assuming maximization, we see an optimal way of how to choose the search radius with respect to the fitness. So if the fitness is very low, we are far away from an optimal solution. We want to have a rather high search radius, and the closer we get to an optimal solution, the smaller the search radius should be. And in general, we call such a rule a policy, so a function that maps states to a search radius. Now in the example we used a lot of different search radii, which might not be realistic, one might have a limited budget. So in the paper we extend these insights into general subsets of search radii, like for example the subset 1, 5 and 17, and we call each such subset a portfolio, and we state a way of how to compute an optimal policy for a portfolio. For example, 1, 5 and 17 would have the following policy depicted by this red line. Overall, our benchmarks have several benefits. First, the first realistic DEC benchmarks with exact ground truth. And also they have challenging properties, for example, the uncertainty in the runtime, because each of these algorithms is a randomized algorithm after all. And this also leads to long episode length in the learning process. However, the function itself and also the algorithms are cheap to compute, so that means the challenging aspect overall for these benchmarks is the learning part. And last, they also have highly tunable parameters, for example, the portfolio for the algorithm or the dimension of the problem, or also the initialization strategy of the algorithm. And next, Nguyen will tell you what learning approach we use in order to actually learn optimal policies.
In this part, I would like to talk about how we make use of the proposed LeadingOnes benchmark to study the learning behaviors of a DAC method. And in particular, we will analyze the learning behavior of DDQN, a commonly used deep reinforcement learning approach. DDQN has been applied to DAC settings, including the learning parameter control policy for differential evolution algorithms, and for selecting heuristics in AI planners. DDQN can be seen as a combination of an epsilon-greedy Q-learning method with two Q networks. A Q-learning method is a method that focuses on learning a function called the value function or the Q function. And a value function Q of a policy will receive two inputs, a state and an action. And the function will tell us what is the cumulative future reward the agent will receive if it plays that action at that state and then follows the given policy for the rest of the run. The idea of Q-learning is to find the optimal policy via learning this Q function from the data collected during the training. Now, deep Q-learning is just about representing this Q function as a neural network. And the double Q deep learning uses up 2 copies of such Q network during the learning in order to improve learning stability. As explained by Martin, the benchmark we propose is highly configurable, so we can study how DDQN performs in different DAC scenarios. In the first study, we applied DDQN to 3 different portfolio settings, and we also vary the portfolio size from 3 to 5, but we fixed the problem size to 50 for simplicity. We considered 3 portfolio settings. For the first one, named powers up to, we just use numbers in increasing orders of powers up to. For the second one, initial segment, we take the first k numbers in the range from 1 to n, and for the last one, called evenly spread, we split the whole range from 1 to n to equal parts, and we take the first element of each part. Now what we observe from the results on those scenarios is that DDQN can learn policies that are quite close to the optimal ones. In particular, as shown on the left plot, the performance of DDQN are almost the same as the optimal ones. And on the right side, we plotted the learned policy and the optimal ones. And we can also see that policies learned by DDQN are very similar to the ones suggested by theory. But that's not the end of the story, there's a but here. So actually the learning behaviors of DDQN during the training can vary widely among the 3 portfolio settings. Here we plot the performance of the learned policies during the training. The points with close to optimal performance are marked as green dots, and on the left we show the training performance for the evenly spread setting, and on the right it is for the initial segment setting. We can see that the learning on the left side is quite unstable, with performance of the current learned policy keep jumping up and down even at the very end of the training process. while for the right side, we see that the learning of DDQN seems to be more robust. To quantify those observations, we define two measurements for the learning progress. The first one is the hitting ratio, which tells us how often we reach the optimal policy performance. And the second one is ruggedness, which measures how unstable the learning is. And here's the measured values for all three portfolio settings. We can see that both hitting ratio and ruggedness of the three portfolio settings can be quite different. For the evenly spread setting, the hitting ratio are generally higher, but the learning is also less stable. While the initial segment has lower hitting rates, but the learning is generally more stable. So this poses interesting question on what is the characteristic of that scenarios that can impact DDQN learning ability and whether we can improve the learning in those settings. Also, another thing we observe from those plots is that when the portfolio size K increases, the hitting ratio also decreases and the learning is less stable, which suggests that DDQN starts struggling to learn when it has more actions to choose from. So we will investigate this point further in the next study. In the second study, we look into the impact of portfolio size and problem size for the learning ability of DDQN. The plots on the left side show the hitting ratio for two problem sizes of 50 and 100, and we try different portfolio size from 3 to 20. It is very clear that when portfolio size goes up to 15, the hitting ratio becomes very small, and this is particularly true for problem size of 100, where the DDQN agent is no longer able to learn. We also see similar scalability issue when we increase the problem size to 200. DDQN can no longer learn even with a small portfolio size of 5. Those are the limit points of our current DDQN setting, and there are definitely rooms for improvement and further study. So far we have seen that the proposed benchmark is useful for getting insights into the learning ability of DAC methods such as DDQN. Now I'll hand it over to Carola for some other interesting insights from the theoretical point of view.
We have now seen that our benchmarks are useful for the study of reinforcement learning, but they are also interesting from a theoretical perspective. Let me give you an example. We can ask ourselves, for a given portfolio size, what is the optimal set of actions that we can propose so as to minimize the expected optimization time of an optimal policy. This is what we did here for problem dimension 50. We see that if we are only allowed to choose 2 different actions, the best we can do is to choose 1-bit flips and 4-bit flips. We computed these optimal portfolios for a number of different portfolio sizes, and here are the results. When we look at the result, we observe the first pattern, and this is that up to 1/2 of the portfolio size, the whole initial segment of possible search radii is chosen. And this set is then complemented by some numbers that grow much more quickly. This pattern does not only hold for this particular problem dimension, but when we increase the problem dimension, we see very similar numbers appearing again and again. Sometimes the numbers are a bit different. And to be honest, we don't quite understand at the moment what the optimal portfolios look like. So this is an exciting research question for us theoreticians, and we hope to be able to tell you more about this in a future GECO. Let me now summarize our work. We hope that we could show to you that DAC is a really promising and exciting research direction. It combines parameter control with AutoML techniques. DAC is a very young field, and we believe that our benchmarks help to get DAC right from the beginning. We have also seen that DDQN, one of the default choices, actually performs quite well. We have also seen certain limits of DDQN, and in our future work, of course, one of the first things we want to investigate is the sensitivity of DDQN with respect to its hyperparameters. We also want to study different RL approaches. And one of the key questions that drive our research is whether the reinforcement learning agents are able to learn policies that generalize across different problem instances or even across different problems. We believe that it's also useful to use more information to describe the current state of an optimization process. And in order to leverage the full potential of reinforcement learning, we think that we need to use advanced techniques such as auto-RL, tempo-RL, and self-paced learning. I already mentioned that there are a lot of theoretical challenges for us as well that we plan to attack in our future work. This brings me to the end of our presentation. We hope that you have enjoyed it. We hope that you agree that DAC is a very exciting research, and we'll be happy to chat. You can grab Martin, he is attending Gecko in person, and the other 4 of us, we're attending virtually, and we'll always be happy to discuss our work. Thank you very much.